Hi, my name is Ruppa-Kasani, and my science fair project is the detecting and imaging of triple-negative breast cancer using water-soluble perovskite quantum dots. And I chose triple-negative breast cancer because it lacks the three main biomarkers that most breast cancers have: estrogen, progesterone, and excess HER2 proteins. And without these biomarkers, scientists have a hard time detecting it in its early stages and can only detect it later with mammograms, MRI scans, and ultrasound. So you can't just detect it later like that, or else the patient will already die. The cancer would have already metastasized, and there's no way to save the patient. Because like triple-negative breast cancer has a mortality rate of 23%, which is 16% higher than other forms of breast cancer. So the best way is to detect it in its early stages, and that's my goal to do this. And I do this with luminescence, but I'll be getting into the whole luminescence field later. And right now I'll be going into what I actually detected. I detected the cancer exosome. And I detected the cancer exosome, which is basically a cell-derived vesicle that comes from cell to cell, transporting proteins and other things like that, just for like the cell's life cycle, kind of like that. And you have to know that when there is a cancer cell, there will also be these vesicles and these exosomes. And so the whole point of me detecting the exosomes is because it is abundant in biological fluids, and therefore there's no margin of error that could ever occur, and I could immediately detect the cancer exosome with my luminescence. And luminescence. You always hear me saying that, and I use the perovskite material to actually produce this very bright luminescence. And I chose the perovskite material because it has an extremely high photoluminescent quantum yield, which means the amount of photons that enter the perovskite substance is almost the same as the photons that exit it as luminescence. And because of this extremely high quantum yield, I use the perovskite material because I need a very bright color to actually know if the exosome is present and if the sample actually has triple-negative breast cancer in it, right? So with perovskites, another perk is that you can easily change its halide combinations to form different colors. And in my experiment, I had bright blue, bright red, and bright green perovskite quantum dot color. And you can just, by varying the amount of halides, you can change the color in like the entire visible spectrum. You can get all the colors. So now I'll be getting into the main problem with perovskites, and that is its stability. Perovskites degrade in ambient conditions, like due to the moisture and air in the environment, and this is extremely bad, especially if I want to use it in biological settings. So I must make the perovskite material water stable. So there has been previous efforts to make the perovskite material water stable, such as metal oxide coatings, inorganic encapsulation, inorganic films, but like all of these don't give long-term stability and is not very reliable. So the whole goal of my project is to make another way of making the perovskites water stable, and I do this through polymer coating. But I'll also get into that later when I'm describing how I actually polymer coated the quantum dots. So now I'll be getting into my procedure. So the procedure goes as follows. I had a cesium oleic precursor solution, which I made using cesium carbonate, oleic acid, and 1-octadecene. This is heated and mixed under nitrogen gas and mixed with lead bromide, oleamine, and 1-octadecene. The lead bromide is only for the green luminescent perovskite quantum dots, but for red and blue, there are different kinds of ratios of lead bromide, lead chloride, and lead iodide you can get. For example, for the red perovskite quantum dots, you have to have the 2.5 to 1 ratio of lead iodide to lead bromide. And like in the blue perovskite quantum dots, it was a 1-to-1 ratio of lead bromide to lead chloride. So there are different kinds of ratios of these like halides, and from that you can get like all the colors in the visible spectrum for the perovskite quantum dots, which makes it even more versatile. So now I'll be getting into the results of my synthesis and the results of my experiment. Now here you can see the emission spectra, the fluorescence emission spectra of all my perovskite quantum dots, and you can see how the lambda max wavelength obviously matches the actual color of the perovskite quantum dots, and so like for example, like green perovskite quantum dots had a lambda max wavelength of 516 nanometers, which is good for a green green material, because obviously green on the EM spectrum is 516 nanometers, which shows that the synthesis is actually successful. The TEM images. This was a very nice TEM images because there are very uniform cubes in the TEM images, and like it has a 5 to 15 nanometers range in like size. So that's extremely good for quantum dots, because like quantum dots about like 10 nanometer in size. So these were like very successful perovskite quantum dots. So now I'll be getting into the polymer coating. This is my method of making the perovskite material water stable, and therefore it could be used in biological settings. So I use polaronic F127, which is a commonly used polymer in biological settings. And I chose this polymer mainly because it's amphiphilic, and which means it has a hydrophobic and a hydrophilic end. The hydrophobic end goes and attaches to the perovskite quantum dots, but it's not really attaching, it's kind of a non-covalent interaction. It also has a hydrophilic end, which is good, obviously, because it makes it water stable. And with this hydrophilic end, you could obviously put it in a biological setting and it wouldn't degrade. So like, then I took some more results after I polymer coated it, because it was kind of a part of the experiment. Then I got the TEM image of my polymer coated PQDs. Just like, I'm just saying that I only use the green PQDs for this because the results will be the same for like red and blue. So I only took the green PQDs, and you can see like in the TEM image how it definitely increased in size because it's 30 nanometers now. And because obviously that's expected because you added a polymer to it, obviously it got bigger. And I also took an X-ray diffraction of this to see if the cubic structure actually changed. But here you can see that both of the XRDs have stayed the same, so which means that the cubic structure has been retained from before polymer coating and after polymer coating. Then I'm going to get into, I also took another graph, which is the stability of my PQDs in water. This is an extremely important graph because it shows how stable my polymer coated PQDs are actually are. And it shows that how my polymer coated PQDs, they stayed, this shows the intensity over time of my PQDs. The orange line shows the my non-polymer coated PQDs, the blue line shows my polymer coated PQDs. The orange line degrades almost immediately, and this is extremely, as I said before, the perovskite material degrades in ambient conditions, and that's clearly represented here in the graph. But with the polymer coated PQDs, you can see how it only degraded significantly after maybe 8 days. So that's extremely good for my polymer coated PQDs. So the polymer coating definitely worked. So now I will get into the actual antibody conjugation of my perovskite quantum dots. So I use the anti-CD63 antibody because it's specific to the actual triple-negative breast cancer exosome. It's because I need to use something specific to that, obviously, so it can go attach to the exosome. And basically, what I did, it wasn't any sort of actual reaction that I did. It was just some kind of non-covalent reaction. I just mixed the antibodies with the perovskite quantum dots and sonicated it, and that was basically it. And so the main goal of this is for the anti-CD63 antibodies to go attach to the perovskite quantum dots and go crowd around the perovskite quantum dots, so that when the perovskite quantum dots are added to some kind of sample of the triple-negative breast cancer exosomes, it will go and crowd around the exosomes because the anti-CD63 antibody is present on the perovskite quantum dots. And so basically the whole goal is for it to crowd around the exosomes and give a bright luminescence, because obviously all the perovskite quantum dots have lots of luminescence, and when they crowd around something, that they'll be concentrated in that one area, and you'll see a bright green color. And that's seen in this picture here. You can see in picture B how all the perovskite quantum dots crowded around the exosome, and it gave a very bright green luminescence. And this is just a luminescence microscope image. This isn't any sort of TEM image, and this is just a luminescent microscope image that shows how bright the luminescence of the perovskite material actually is. And in picture A, you can see how the perovskite material really crowded around the exosomes, and you can see the different spots there. So now I'll be getting into my kind of side kind of experiment, so just to test the specificity of my actual perovskite quantum dots. and this is with my the Hakat skin cells. And I basically just did the same experiment, but with Hakat skin cells, and there was no fluorescence at all. It was just a black image, and that shows how the perovskite quantum dots didn't go and crowd around the Hakat cells. Nothing really happened. And that shows how my perovskite quantum dots with the anti-CD63 antibody are really crowding around the exosomes, and it's working specific to the triple-negative breast cancer exosomes. So now I'm going to get into my summary and conclusions. With my project, I accomplished the perovskite material being actually stable in biological settings and water stable. And this is using polymer coating with pluronic F127. I accomplished this. There was an extremely high photoluminescence quantum yield with my perovskite material, and this is why I wanted to use it. And it produced a bright green color, as you can see in the fluorescent microscope image. Stability, this stability graph that I went to, the stability of PQDs in water, the polymer-coated PQDs, it was stable up to 8 days. And even after that, the luminescence will just be a little bit lower, but it's still producing that bright green luminescence. But it's stable up to 8 days, which is extremely good. And the anti-CD63 antibodies are specific to the triple-negative breast cancer exosome, as seen by the Hakat skin cell experiment. So for some future studies, maybe I could covalently bond the antibodies to the perovskite quantum dots, or the polymer to the perovskite quantum dots, to make it even more stable, more than 8 days. And this could be some sort of peptide bonding. I'll have to do more research in that field later. Also, perovskite materials are mostly used in solar cells. So I could do maybe some future research in actual solar cells and how much they can be used in these solar cells. So those are some future studies. Thank you for listening to my presentation.